Um, we can just go ahead and get started as folks are coming in. So hello everyone again, and welcome to day 2 of the IRTOC workshop hosted by the DOE Grid Deployment Office and the National Renewable Energy Lab. Again, my name is Amy Levy here at GDO. And we'll go over a few things before we get started today. So none of the information presented herein is legally binding, and the context included in this presentation is intended for informational purposes only relating to the Interregional Transmission Operational Coordination project. And the purpose of today's meeting is to ask your input regarding IRTOC topics. And to that end, it would be most helpful to us if, based on your personal experience, you provide us with your individual advice, information, or facts regarding this topic. And the objective of this session is not to obtain any group position or consensus. Rather, NREL and GDO are seeking as much input as possible from all individuals at this meeting. And to most effectively use our limited time, please refrain from passing judgment on another participant's recommendations or advice, and instead concentrate on your individual experiences. And this Zoom call is being recorded and may be posted on DOE's website or used internally. If you do not wish to have your voice recorded, please do not speak during the call or disconnect now. If you do not wish to have your image recorded, please turn off your camera or participate only by phone. If you speak during the call or use a video connection, you are presumed to consent to recording and the use of your voice or image. Yes, if you have any technical questions, you can type them in the chat box and select send to Tim Meehan. You can also send him an email at timothy.meehan@nrel.gov, and he can put his email in the chat for reference. And today we'll again be using the Q&A function within Zoom. So we encourage you to ask questions during the workshop, and you may ask them during the question and answer box. And we'll also address questions at the end of the session. So you can also unmute and ask questions during that time. The Q&A and discussion portions of the meeting will not be included in the recording. So for our agenda for the day 2 of our workshop, I'll give a quick recap of what we went over yesterday, and then we'll have a couple folks from NREL give an overview of the National Transmission Planning Study, as well as the barriers and opportunities for interregional transmission paper that they just released a week or 2 ago at this point. And then we'll have Yang-Han give a talk on post-transmission, which is more information on the IRTOC project, as well as some discussions from a couple of folks on the IRTOC software development and case studies. And then at the end, we'll have an open discussion to hear your feedback on our methods, as well as our approach and preliminary results. Yes, and yesterday we had just a quick kickoff. We had heard from a few experts on their North American experience sharing from MISO, ISO New England, as well as the operator in Ontario. We also had heard some information from the European experience on multi-region market coupling. We heard from experts on that. And then we also heard our initial background on the Interregional Coordination Project. So now I will hand it over to David Palchuk to give an overview of the NTP study.
Thank you, Yamit. How are things looking?
Looks good.
Looks good.
Okay, great. Okay, thank you, Yamit. So I'm going to be talking about the National Transmission Planning Study. So this is a study that's been going on for about 2 years. I'm presenting here preliminary results, but we do hope to have this study published in hopefully the summer, the end of the summer, maybe early fall. So I'll be showing some of the preliminary results and talking about some of the kind of motivation behind it. So this was a partnership with the Pacific Northwest National Lab and the Grid Deployment Office who funded the study. So the objectives of the study were to simply kind of better understand the role, value, and opportunities for transmission across the U.S. There's some specifics about that that are important. One of them is that we're really focused on the interregional and national strategies. I think interregional being the kind of important emphasis there. Trying to add to what the stakeholders are doing in the regions and offer some different solutions or additive solutions for those processes. So we did engage a lot of stakeholders along this study. Hopefully many of you were probably part of this, and we really appreciate your involvement. And we certainly wanted to be additive to what's going on in industry. As is often the case with lab studies, we also want to develop new methods and provide some kind of innovative feedback for the industry about the best state of the art, as well as develop some innovative methods. So the way we approached looking at transmission for the U.S. was using several different models to understand low-cost, reliable transmission systems of the future. We did this in really two different resolutions. I think a lot of these kind of models will be familiar to many of you. So in the blue, we have our zonal resolution, and this is where we're really looking out across many scenarios out to 2050. And we do that at the zonal resolution, partly for tractability, as well as we're putting a lot of different details into things that aren't spatial. We're using policies, we're using different demand scenarios and building out a lot of different future grid scenarios at a zonal resolution. So this map kind of shows the resolution of at least the transmission system. And so we use capacity expansion models. That's kind of the base model that we use to build out our scenarios. We also do some additional economic analysis and some resource adequacy kind of deep dives within our zonal kind of world across many scenarios. We did almost 100 scenarios for the study. And then we move over into the nodal resolution. And this is where we do a lot of painstaking translations as well as transmission planning to some extent, at least as much as we can, to get into our production cost models. And we do this for only a couple scenarios. This is quite difficult, and we get quite detailed. We use network models, and we build out production cost models, power flow models, as well as do additional stress analysis with these nodal scenarios. I'll show a couple maps of what we came up with. These are, we call them transmission portfolios. Ultimately, we're looking for implementable solutions, to sort of validate what we find in our zonal world. Certainly not anything, plans of service or anything of that sort of thing in our nodal world, but we're just trying to test our systems and make sure that, these are implementable and address some of these engineering challenges that planners would face. So we do that for a few scenarios, and I'll show some examples of that. Overall, we're trying to really kind of get a lot of scenarios, understand the challenges in the future, and come up with several good solutions, hopefully. So as we build out our scenario framework, the most important part of that is our different transmission frameworks. So you'll see these four transmission frameworks referenced in the coming slides. So I'll take a minute to explain them. So our limited is our reference scenario. So in this scenario, we're basically trying to limit the amount of transmission that can be built across the US. So we don't allow any new interregional transmission. When I say interregional, I'm referring to the FERC 1000 plus ERCOT regions, so 11 different regions in the US. We don't allow new lines across those interregional seams and the black lines there. We're also limiting the total amount of transmission to recent observable maximums. You'll easily see this in some of the results. We're looking at essentially the last decade, the last 15 years, looking at what was the maximum observed and limiting the total amount of transmission that can be built in our capacity expansion model in this scenario. And in our accelerated transmission frameworks, so there's three of them. The alternating current or AC. So in this one, we're allowed two maps. You can see between limited and AC, you can see that we removed all those interregional lines. So we're essentially allowing AC to be built within the interconnections, no new DC connections in this case, but we're allowing as much transmission as is cost effective. And our bottom two are HVDC scenarios, so two different flavors of that. So our point-to-point. So that's essentially using more traditional HVDC, and you'll see that referenced as LCC, or at least that's the cost that we use for these lines. And you see these as potential options on this map here in these orange lines. This is not what eventually gets built. This is just what the model could see as potential new options that weren't available within AC. And then in our bottom one, our multi-terminal, this is more of a meshed ready sort of grid. So adjacent zones can connect here, as well as some additional zones. And expansion is allowed across the country in our two HVDC scenarios. So you're seeing this across the three seams between the eastern, western, and ERCOT interconnections. And so sometimes we'll refer to those as just our HVDC scenarios. So those are the four transmission frameworks or paradigms. To expand our scenario matrix, we're also bringing in different demand growth. So in the top right corner, you see three different demand growth: low, medium, high. And this essentially goes up with more electrification of the system. So you'll hear me mostly refer to the mid demand in this presentation. In our high scenario, this is a lot of electrification by 2050. And so this is high is about 3% growth, mid is about 2%, and low is about 1% growth nationwide. We also look at three different emissions targets. So the current policies is essentially what was in the books by last summer. So any of the state RPSs, as well as Inflation Reduction Act. Anything that was law by last summer is in our current policy scenario. We also have two emissions target scenarios, so 90% CO2 reduction by 2035, as well as a 100% by 2035 target. So that's the White House target, but not a law. So these are just our different decarbonization scenarios as well for the emission target. So this is 36 total core scenarios, and this can be a little bit confusing. Ultimately, we're trying to get a sense of the future and understand the role of transmission across these many possible futures. So I'm not going to go into a lot of results on all of these, but this is how we set it up, and a lot of our results kind of pull simple, common findings from all of these. So for the next few slides here, I'm just going to focus on the 90 by 2035. So in the top right, you can see what that means for emissions. So the black dots show historic emissions. You can see that's been going down since about 2005, 2006, mostly driven by the changeover from coal to gas. And if you follow the purple line, which is our emissions trajectory in our model, it's a little bit steeper than that. But by 2035, we get to 90% reduction from 2005 numbers, and then 100% by 2045. And I'm going to focus mostly on the mid demand, as I said. And again, there's the demand chart. So we call this sometimes our central decarbonization scenario as well. So I might refer to it as that. So a couple of results on this specific scenario. So first of all, we see a lot of transmission built when we allow it to be built. So there's rapid and significant growth under our decarbonization scenario. So here you see the transmission capacity for our four transmission paradigms. In our three that we allow to build, the AC, the point-to-point, and the MT, we're seeing 2.4 to 3.5 times the 2020 capacity, and we're seeing more in our HVDC scenario than our AC. The blue line here, again, I said I'd point that out. So that's our limited scenario, and that's basically following observed transmission additions from the last decade. So following that out, and it's building as much as we allow it to build. It is using all of that capacity, most of that in local interconnection capacity. So we are capturing what it takes to kind of connect a lot of different resources. So we see spur and reinforcement mostly used in that limited scenario. But all types of transmission are observed for all these scenarios. It's all important. We do capture the local interconnection cost as well as some of the higher voltage interregional lines. And I'll show some maps of that. So showing those examples actually that I just showed on the map. So if we look at our three accelerated transmission frameworks, we see transmission built essentially all around the country. But we do see some concentrations in the middle of the country, as well as some other kind of obvious trends. We see some southern trends as well as some kind of north central trends that kind of persist across all of the scenarios. So a lot of different common examples here that hopefully we've learned from, and I'll show an example of how we tried to distill that into some lessons. But a lot of transmission built, a lot in the middle of the country, a lot of it to move wind and solar to load centers. When we look specifically at the interregional transmission, we see it means different things for different regions. So this plot here
somehow cannot hear David. Can you?
Excuse me, Yohan?
Oh, we lost you for a little bit.
Oh, okay. Am I
Now
back?
you're back. Yeah, you're back.
Sorry about that. Okay, so this plot, I'll just start over on the slide then. So this plot is showing the 11 different regions, the FERC plus ERCOT regions, and it's showing the transfer capability over the peak demand. So as you can see in our limited scenario where we don't allow any interregional transmission to be built, that goes down. That's because demand is going up and we're not allowing interregional transmission to be built. If you look at the AC scenario, we're seeing in many of the regions, it's basically maintaining the current transfer capability over peak demand fraction. In some regions, you are seeing, in West Connect, SPP, and MISO, as well as a few others, you are seeing an increase in the total amount of interregional builds for those scenarios in reference to the peak demand. As you go to the HVDC scenarios, you see some dramatic changes where a lot of interconnection is being built compared to the amount of demand in the region, especially West Connect, SPP, and MISO reaching over 1.5 for several regions. The other one of note here, ERCOT, so we aren't allowing connections across the seams in anything but the HVDC scenario. So you can see that it goes from a very small amount of interregional capacity to a relatively, a lot more relative to what it was in our AC and our limited scenarios. So a lot of transfer capability being built, especially for some of these regions compared to the amount of demand. Kind of an interesting metric there to look at. If we zoom in further at what's happening across the seams, essentially when we're allowing transmission capacity across the interconnection seams, we're seeing a huge amount built. So this is just looking at our HVDC where we allow the interconnections across all three seams, and you can see that we're increasing that by 35 to 50 times the current seam crossing capacity in these scenarios out to 2050. And you can see these lines highlighted here, the ones that actually have the colors. So just to explain here the charts a little bit. So we break up our different HVDC technologies, as I said, into the LCC and the VSC. And you can see them highlighted here on the map. And so they're also the back-to-backs that are expanded in some cases in the point-to-point specifically. So a lot of seam crossing capacity built when we allow it, and especially when you compare it to today's. So why is there so much transmission built? Well, basically it saves money. So approximately $1.60 to $1.80 is saved for every dollar spent on transmission in our 90% scenario. That amounts to about 270 to 490 billion compared to our limited scenario where we're not allowing transmission to be built. The other thing you can notice in this plot here, so we've highlighted our core scenario that was represented by the 90% mid-demand scenario. This also shows all the sensitivities around those scenarios, and I'll show a list of those sensitivities here on the next slide. But ultimately, what you're seeing is across many of the future scenarios that we're looking at, we are seeing savings when you're allowing transmission to be built. And so that's represented by these gray lines and the light-colored bars as well. So pretty consistent message that you get savings with transmission. So in addition to our core scenario, so that's represented by the transmission and the demand and the emissions targets in the top right, we also ran 15 sensitivities on our 90% case, just to make sure we understood the different pieces of uncertainty and how that we can pull lessons from that. So you'll see references to cost a lot on this table. So we're not going to go through all of these, and I don't think that's necessary, but you'll see references to cost. We changed cost on a lot of different technologies. If you go to the bottom, you'll also see, we changed availability of different technologies. Some, maybe nascent technologies in the case of H2 and CCS or new nuclear. So taking those technologies in and out to see what impact that has on the role of transmission in the future. And to just kind of fly over what that looks like. So the spatial distribution of transmission is robust across a lot of these sensitivities. So the core scenario in the top left is what I showed previously for the AC paradigm. And if you look across all of these maps, this is the sensitivities of that paradigm. And kind of at a high level, one of the good things is there's a lot of common solutions here that gives us some confidence that a lot of the solutions that we can come up with and distill from this would be common in many, many futures. So that's kind of one of the reasons we look at these maps and run all of these sensitivities, is to try and pull out the lessons across many of them, as well as some of the other additional lessons where you get down to the bottom row here, where we don't have some of the technologies. Transmission has the potential to become even more important in those futures. But certainly a lot of variation in here as well. So when we take all of those maps and try to distill them into a single map that we can actually move forward with, what we get is this. We call this the high opportunity transmission. So this is showing the new interregional transfer capacity that was essentially robustly developed across our sensitivities. So we cut off this number with, it had to be in 75% of the sensitivities I just showed. So if it wasn't 75% of them, it made it onto this map as our high opportunity transmission interface, just to give some perspective on how big the transmission still is, even with that somewhat conservative estimate. If you look over at the PJM East MISO Central corridor, that is about 28 gigawatts now in 2024. They're looking at an expansion out to 2035 in this case by another 12 gigawatts. So a pretty large expansion. And then if you look out west in the Northern Grid South and West Connect North connection, it's about 2.5 gigawatts now, and they're looking at additional expansion of 6 gigawatts across our sensitivities. So still big expansions and a lot of opportunity here that is robust in a lot of futures. So I'll quickly go through a couple examples of our nodal scenarios. So we ran 3 different scenarios nodally. It's quite intractable to have all 100 scenarios modeled, but this is really just to do some detailed kind of transmission planning and look at the engineering challenges of implementing these solutions. Certainly not a plan that we expect or is not a plan for the US, but really to try to validate and test our solutions. And also look at analysis of grid operations, the scheduling challenges and the balancing challenges as well. Get some insights about how these futures could look. So these are our 2 nodal implementations of the AC and the MT HVDC. So that's kind of our HVDC scenario in this case kind of encompasses characteristics of both of our HVDC scenarios. And ultimately, you see a lot of transmission, new transmission built. That's the highlighted lines here. A lot of 500 kV in our AC case, as well as some additional voltages, largely maintaining voltages within regions in some cases. And then our MT, getting into kind of a very transformative scenario in this case, a lot of connections across the seams, across the east, west, and into ERCOT from both interconnections. So kind of very interesting implementations here. Ultimately trying to examine some of the engineering challenges and the operations and validate that these systems that we're looking at that are sometimes transformative are implementable when you start to get down into more detailed modeling. But again, just in the modeling phases here. And to just take a look at the different operations for this. So this is something that we created just to kind of get a bigger picture of the nation here, because it is difficult to plan across the whole US. And as you watch this, you can see the sun coming up and the solar coming up. This is 2 days snapshot in March. And you can see the changes on the transmission that's happening. And we use this to try and quickly assess what's going on around the country as we build out these very transformative scenarios, and understand where is transmission needed when we're building such transformative scenarios. So a tool for us, and also kind of a pretty picture of what's going on around the country and how the transmission system is changing. So just to summarize here, so there's rapid and significant transmission expansion, and ultimately the HVDC scenarios build the most transmission. There are a lot of common transmission solutions, as we saw, and then the detailed modeling helps to validate that these are implementable, at least to the extent that we can model them, in those few scenarios. So I'm gonna stop there.
Thank you, David. I think we have one question from Phil McKay that we can probably answer right now. Just to clarify, this study does not include Canada or Mexico.
We have it in our models, but we are not looking at any detail at Canada or Mexico, or making any changes to the systems, but we do have it in our network flow models.
Thank you. I think that was it. So I'm gonna hand it over to Christina.
Great. Hi, everybody. Can you see my screen here?
Yes.
Yeah.
Okay, great. So hi, my name is Christina Simeo, and I'm going to talk about the report that was recently released on the barriers and opportunities to realize the system value of interregional transmission, and this is part of the NTP portfolio. So basically, the motivation for this study is, why might interregional benefits identified in planning models be different than the benefits observed in practice? And here we're talking about benefits like adjusted production cost savings. We identify these issues and opportunities where they occur, for example, between non-market areas or market to non-market hybrid areas, trades between market areas, or issues that are common to all areas. The report tends to focus on historical data and issues with existing interregional transmission, other than the transformative actions section. And most of these issues and opportunities are identified by others. We also identify some of the potential symptoms of inefficiencies, like uneconomic flows from high to low price areas, high price differentials, underutilized capacity, and lack of transparency. Although lack of transparency on inefficiencies is not really a system itself, it's more of a characteristic of bilateral trading areas where there have been historic concerns with rate pancaking, trade friction, limited real-time scheduling options, and use of more expensive resources. So just making that clarification. So maybe less relevant to this group are the barriers and opportunities between non-market and hybrid areas. To address the inefficiencies in bilateral trading regimes, balancing authority areas could implement coordinated scheduling or consolidate to an RTO-ISO. To address inefficiencies related to imperfect congestion management methods like transmission loading relief in the east or qualified paths in the west for unscheduled flow mitigation, balancing authority areas could implement joint operating agreements with neighbors, to have similar congestion management programs, or interconnection-wide integration of paths and other methods. Beyond Order 890 and Order 676I, consistent methods and assumptions for available transfer capacity calculations between neighbors could be required. To preserve reliability over market opportunities in emergency situations, there could be flexibility to adjust scheduling priorities to preserve reliability for native loads. This is an example of this would be the wheel-through priority for reliability imports in CAISO. Moving on to barriers and opportunities between market areas. We heard yesterday about the coordinated transaction scheduling systems that have been established in joint operating agreements between market areas. These programs tend to have real-time prices that are volatile and hard to forecast. These could potentially be replaced with intertie optimizations. Transaction fees could be eliminated and forecasting methods improved. Issues with market-to-market congestion management programs, such as stale firm flow entitlement assumptions or inaccurate constraint modeling, could be updated and automated. Problems associated with the differences between the interface where a transaction is scheduled and the interface where the transaction flows and is priced could be addressed with updated methods and transaction validation. Currently, FERC requires merchant lines to make unused transmission capacity available to third parties and encourages this capacity to be made available to the market operator, but this doesn't often occur. CAISO's subscriber participating transmission owner model facilitates this by allowing CAISO to collect fees and remit to merchants for use of available transmission capacity. Barriers and opportunities that are common to all areas. Deliverability uncertainty for external resource adequacy resources could potentially be addressed through a guidance framework. Large power transfers during extreme events can lead to atypical flows and potential reliability issues. Joint studies could occur to better understand and anticipate system-to-system issues and develop operational practices to mitigate these issues. In addition, there's opportunities to evaluate the internal system to understand where these atypical constraints occur during large power transfers that impede required imports or exports, and then how to manage those atypical constraints. And then lastly, some final thoughts. Improved coordination in the planning, scheduling, and real-time operational horizons could lead to greater utilization and efficiencies. These are transformative actions that are listed on the screen. While the benefits of these transformative actions could potentially be significant, and one only has to look at some of the studies documenting the EU single market integration benefits as an example, these are technically and politically complicated issues that impact stakeholders in different ways, and this report did not explore those complicated dynamics. So with that, thank everybody and turn it back over to Yaman.
Thank you. If there's any other questions, we can take them now. Otherwise, we can move on to the next portion of the day, which Young-Han will give an overview of the IRTOC project, which is currently focusing on congestion management.
Yeah, can you hear me now?
Yes.
Okay, yeah. So good morning. Thank you for attending this workshop, and we hope to hear your feedback and advice. So this IRTOC project is sponsored by GDO, so we are very thankful for GDO to support this important topic. It's a 2-year project started last October, so we're about 8 months out of the total 24 months kind of project timeline. Today, I'm going to me and after me a few team members will dive more deeper into the our progress and first of all the background and the scope. So like Yami said, currently this project focused on the congestion management. Yesterday we had a kind of like an overview. So for the interregional coordination problem, there are many different components. So if you have a different combination, you could have like 12 different possible ways to really construct the coordination method. But here we focus on the congestion management. So there are 4 key areas. First is in the real-time market-to-market congestion management challenges. First of all, we kind of focused on the coordination between market areas, because the methodology is kind of driven by the market clearing, the optimization, and then this method can also be extended to non-market area if they also run security constraint, the unit commitment, or economic dispatch. But for other non-market area today, it's like congestion is mostly handled by like transmission loading relief. It's a quite different methodology. So our project will not kind of get into that area. It's more still within this market framework. And then, so yesterday we kind of heard all this discussion from North American grid operators. So this M2M congestion management is implemented between MISO PGM and MISO SPP. Actually, I worked at MISO for over 20 years before I joined NREL last summer. So about 15 years ago, we implemented this real-time market-to-market congestion management, between MISO PGM. This certainly brought significant benefit for real-time operations. Later on, it's also implemented between MISO SPP. But in today's world, most of the time, there's only one constraint activated in real time. It's definitely, this methodology, if you have a lot of interregional transfer and more kind of binding constraint across the border, this methodology, needs really to be investigated more, just to make sure there's a good convergence. Because even today, with there's a few constraints across the border, it can run into convergence challenging, and sometimes they call it pulse swing. Basically, some oscillation can happen. And then the second part is on the value and needs for coordination in the operational forward process. It's basically in the day ahead or intraday time frame. Yesterday, we heard from our European colleagues. Europe they want kind of a different way. It's not, sounds like it's like it just organically happened, for this multi-country, they figured out the benefit, for cross-border trading. So this EU model is like a very large scale, but simplified zonal approach. So David mentioned, all these future expansion possibility across the country. If we build all these interregional AC line, or especially HVDC, how should we schedule them, right? So if your scheduling is still happening within each kind of a grid operator or RTO, it's difficult to get like an optimal solution for these interregional transfers. And then the third part is really getting into the intra and the interregional HVDC optimization. So there's some RTOs implemented the intra-regional, basically within this RTO region, the HVDC optimization. It's mainly for, HVDC can relieve the congestion in the AC system. And then by optimizing the HVDC, it can improve the reliability and the efficiency. But across the border, so they will be involved. It will involve the kind of a part of the interchange or optimization, right? So it's much more complicated because there are two entities involved. If this transmission is only optimized by one side, you end up with the similar issue. It may not be scheduled optimally. Then the last one is on the reserve deliverability, both intra and interregional. So when I was at MISO about maybe 12 years ago, there's some reserve transfer issue. Basically, the reserve can clear in a region, in a sub area, it's behind the congestion. And then if you need that reserve, really it cannot be delivered. And then at MISO, we implemented this called post-reserve deployment constraints, really trying to formulate the constraint with both energy and the reserve deployment flow, and then make sure the reserve can be pushed to the right location. But this one was not implemented for constraint across the border. So in reality, like between two RTO, the deployment of reserve from both sides can impact the flow across these two regions, and then you need to make sure that this need to be considered, and then when reserve deployed, the system is not over limit. So basically, to summarize the three kind of focus area, the first is M2M market-to-market congestion management on extra high voltage AC lines. This three sub-area enhance the real-time coordination method to improve flow and price convergence. Then the coordination among more than two entities. So in the existing market-to-market construct, it's only implemented for two areas. Basically, if you have more interconnection, the transmission line flow can be impacted by multiple areas. So, there's certainly needs to look at beyond the two entity. And then the third one is basically in the forward process, like day-ahead or intraday. Then the second focus area is HVDC optimization, like I just mentioned, and especially also in the forward process, how we can schedule HVDC efficiently. But when getting into real time, it may need to be adjusted based on the system condition change. And then finally is the ancillary service deliverability, both the inter and the intra-regional. So the next slide really is trying to say the single RTO co-optimization, right? It really brought significant benefit. That's we all understand. So on the right side, I showed some kind of benefit analysis from MISO and PGM. So both kind of indicated that the market brought like $4 or $5 billion a year benefit to the footprint. And then of course, it included both planning and the operational side. So if you look at the energy entry service, MISO benefit is about $800 million a year. PGM is, the energy production cost is $600 million. So they're a huge improvement. So this benefit is compared to with market and without market, right? So Christina mentioned a lot of these themes issue, but if you kind of consolidate this kind of small country area into one large RTU, there's a significant efficiency gain. The RTUs really co-optimize this system-wide constraint like power balance, transmission constraint, reserve requirement, and finally, this is some relatively new development on the flow considering reserve deployment. But now the question is across multiple RTO region or between RTO and non-RTO, today they're definitely, Christina already mentioned that a lot of opportunity for improvement, right? But after we, especially in the future, build interregional transmission lines, how should we schedule? And then, if we don't schedule them well, you could, will not be able to leverage or maximize all the benefit of building these lines. Yesterday we discussed just the center around this fourth set of system-wide constraint, you could have different configurations. Some of these actually happened as the industry transition to like nodal market. For example, like C3 is only consider energy like power balance and transmission constraint. That actually was the structure when MISO first started. Each of the local balancing authorities still kind of manage their reserve. So MISO basically clear the market and then send the net schedule interchange to each of these LBA, and then they will still run their own AGC and the procure reserve for like power balance and for the AGC, balancing authority function. And then so but of course, the most optimal configuration would be the C11, basically a single entity can optimize everything together. Like, the EU model is kind of simplified using a zonal approach. And then there's some development like energy imbalance market happening at California. And they basically, CAISO and these other entities, they jointly clear and basically optimize all these results and considering transmission constraint together. So our project focuses on the congestion management. So it's really the C2 and C8. C2 is basically the current market-to-market the joint agreement between MISO SPP and MISO PJM. So really today it's only considered the energy flow. So if you have call it a coordinated flow gate, that flow gate was identified for all these transmission constraints. If it can be impacted, have large impact from both sides, then it will be identified as coordinated flow gate. And then when this flow gate is violated or binding in real time, the monitoring RTO can activate the constraint and then basically request the other side to also provide relief. Then these two sides kind of exchange shadow price, and then also, one side calculate relief request, trying to drive the convergence. And then, but today the reserve component is not considered. So there are times, the deployment of reserve on one side can potentially cause congestion overflow, but this was not considered, in this joint agreement process. So these slides yesterday I mentioned a little bit basically how these entities can coordinate together, right? So mathematically you can formulate the problem and to solve the problem give the best possible answer. But in the implementation side, depending on the business structure, right? For example, if we have two RTOs, the European model is like we combine them together and solve a single large model. But on the US context, if you combine the two RTO and then trying to solve this nodal market clearing model, there could be computational challenge. So when I was at MISO, I worked many years on improving the day-ahead market clearing computational performance. So, today this large RTO, the market clearing problem is already pretty big and complicated. If we combine them, to have a couple of clearing, we have to probably simplify the model. European basically went to the zonal approach, but we all know zonal approach has a lot of problems, right? So basically, in US, all these RTO regions moved away from zonal to nodal. But this single large nodal model, it can give us a benchmark. So we can build that and then evaluate the the computational performance challenging, and then also the economic benefit gained by coupling them together. But even if we can address the technical issue on the computational side, it will require an entity to run this coupled market clearing, right? So that's also it's not going to happen quickly. That definitely will take time, to get consensus on establishing something like that, and then to perform this kind of joint clearing. And then so that's a problem with this approach. Another approach is basically we still have this regional market, and then you can exchange information and trying to achieve convergence. That's basically this coordinated transaction scheduling, interchange optimization, or this joint and market-to-market congestion management is all along that line. So basically say within my current RTO structure, I'll try to exchange some information on the shadow price, and then or some of the relief information, and then hopefully we can exchange information to achieve convergence. But all these method today is implemented in the real time, not really in the forward process like day ahead or intraday. On the day ahead or intraday context, we normally just solve one problem, one large problem at one time, right? So day ahead clearing, you just solve this problem, then clear the market, post the result. So if we want to do the coordination, from that, then you basically need to solve the problem and then exchange the information across multiple RTO, then take that back and then do another iteration until it's converged. So this would, first of all, is challenging on the convergence because they had a forward process involve commitment. Problem is non-convex, and then the convergence can be challenging. And then secondly, multiple iteration even on this sub problem probably is smaller than the combined coupling problem, but still take quite long. If you run multiple iteration, the time can also be quite long. So we feel like this method is probably, first of all, on the algorithm side, need significant effort, to develop a method for convergence, and also on the implementation side for this RTO to exchange all this information on this large market clearing model it's also can be very challenging. So right within this project, we're now planning to study this solution method. So we'll focus on the left side, potentially see what's the benefit of combined coupling, and then what kind of simplification may help us to address some of the computational challenge. But we keep in mind that this approach will require maybe some entity to manage this joint clearing. And then when we get into real time, it's more like a rolling clearing. So normally, within one interval, it's pretty kind of short interval, 5 minutes, right, rolling. And then normally we don't try to achieve convergence within one interval. So like today, for both joint the coordinated transaction scheduling or M2M market, congestion management, both sides can solve the problem. And then after you solve it, you may still observe solution difference, right? Like for example, for the same transmission constraint, the two sides may solve with different shadow price, and that's okay. We just exchange that information and move to the next interval, and then take into account the solution difference on these joint constraints, and then trying to drive convergence. So basically, the convergence can happen after multiple intervals. In the meantime, system condition may also change. Then so this process will take into account all these. Eventually, hopefully it will converge. But there's still kind of challenges, with today's process. First of all, we need to develop methodology or algorithm to drive better convergence. And then also, if we have large number of M2M constraint, right, the joint kind of coordinated congestion, the convergence can be even more challenging. So this hasn't been really looked a lot in the industry. And then also about the coordination among multiple regions. Today it's just happening in 2 regions. So these are like 3 areas we're going to study within this project. Here's the scope and the timeline. So we started last October. Now we are probably 1/3, into the total project timeline. The 3 main components. First is the Sienna software development. Jose is going to talk about it more later. And then, so really, we're trying to develop this Sienna decomposition capability instead of solving like an entire nationwide large problem. Will reflect this regional clearing and the coordination. That this will also be multi-stage, like a real-time is rolling coordination, and with energy and reserve optimization. And then the second part is on the coordination structure and algorithm. Basically, we will build this methodology or solution algorithm for all these areas I just mentioned, like HVDC optimization, reserve deliverability, the M2M flow coordination, and then also develop this multi-stage simulation framework to be able to evaluate these different algorithm or methodology and coordination structure. And then the third area is on the case study. So we started with like a 5-bus and 96-bus system. We have done extensive prototype on these small systems, and then we're in the process of moving to the NTP study model. So Jared will talk more about that. We're not planning to go straight to the national-wide coordination. So we'll start maybe with a few areas such as MRSU SPP or MRSU PGM, and then just look at this future NTP model with this new transmission build out, how this regional operation can impact the scheduling of flow or efficiency on this transmission line transfer, and eventually the final goal is to be able to run this multi-stage simulation with different coordination approach on NTP size model. I don't know how much time I have. So the first is M2M to congestion management on HVAC line and HVDC optimization. So these 2 problems, we can look at them together. It's really just within this security constraint, unit commitment and economic dispatch, how we kind of formulate this constraint, and then if it's across 2 RTO area, you basically have to break that into 2 problems and how to coordinate this common set of constraint across the border. So in the real-time coordination, like this M2M across MRSU PGM, there's a benchmark model basically saying these 2 sides basically still have individual power balance constraint. The interchange schedule, the net schedule interchange will still form the transactions. It's determined outside of the market. Each market clear their power balance equation, and then but they will coordinate on the congestion management. So if there's a constraint across the border, is binding or violated, then both sides can redispatch to resolve the constraint. We're trying to achieve the cheapest redispatch solution. So this benchmark model basically have a joint transmission constraint formulation. Of course, in order to solve this model, you need some entity to have information from both sides. Then you will be able to, build a model and solve this problem and get a single kind of solution. So you end up with a single shadow price for this joint constraint, and that reflects the cheapest redispatch option from both sides, right? And then, but of course, we in reality we don't have that. MISO doesn't know the information from PJM side and vice versa. So the reality is you have to solve them in a kind of distributed way. So there are two algorithms that we developed. One is it's called the distributed control through shadow price. So that was really an extension from existing methodology implemented between MISO PJM and MISO SPP. So we mentioned early this method in production, sometimes it can run into convergence issues. So within this project, we developed some improvement, to hopefully, have a more robust convergence. So we tested it on only small system, and it demonstrated some better convergence with this improvement. And then the second method is on this marginal equivalent. Basically, yesterday, ISO New England also mentioned they developed this method for the interchange, the interchange optimization problem. It's really both sides exchange marginal unit and then incorporate that into their multi-clearing. So we actually also adapt that for this congestion management problem. So we similarly will exchange marginal unit, between each other, and then one side will include them into their transmission constraint, but we'll kind of still enforce basically saying the total redispatch megawatt from the other side will be 0. Basically, we said no change to the net schedule interchange. And then we compare these three different methods, right? The benchmark will give us benchmark, and then the distributed control and marginal equivalent, they both of the methods will require multiple interval to converge to the optimal benchmark result. So this is just summary of where we are and the observation of this method. So this one, like a distributed coordination through shadow price exchange, this one is really purely kind of based on the price, and then you have to guess how much relief the other side can provide. So that can sometimes try and cause some slow convergence. And we tested this method on 5 bus, 96 bus, and also like a small 4 RTO model. And then this marginal equivalent, because you get the full marginal unit information from the other side, so it will give some better convergence. And then, but it's challenging in terms of determining the marginal unit, especially with energy reserve optimization. And also, if the reserve definition is different between two RTOs, that can be even more challenging. So here's some kind of preliminary results on a small system. The C2D is basically the distributed control, and then on top side the C2B is the benchmark model. So you can see the C2D flow, it can be different from the C2B, the benchmark, but eventually it can converge. Similarly for the C2M. And then the second row is on the price. So the benchmark model, because we have a joint clearing, just a single constraint, you have a shuttle price for that constraint. But on these both of these, you know, C2D or C2M, they have two RTOs solving this at the same time, right? The price may not be the same immediately as the benchmark, but after some iteration, it can eventually also converge. The bottom line is in terms of the generation dispatch, you can see the C2B, you know, sometimes it will take quite some interval for the blue lines, basically the solution from this distributed method, you know, to converge to this orange line, which was from the benchmark model. But the marginal equivalent on the right side, it can converge much better. But sometimes it can also take a few interval to converge to the optimal, you know, especially when the system condition change, the marginal unit may change. So if you use the marginal unit from previous interval, it may not converge immediately. So the forward process is much more interesting. Yeah, we mentioned like we're not planning to explore this kind of distributed algorithm because in their head there's just too many constraints. And then, for example, in my so they had it could have 200 some transmission constraint binding, and then if you exchange shuttle price trying to get convergence on all these constraints, it will take significant effort on the algorithm development side, and especially there's also non-convexity involved. So here we're trying to look at, you know, first of all, we'll build the benchmark model, right? And then the C2B, and then, you know, the current practice is normally one RTO. The monitoring RTO will consider that constraint clearing, but it has to estimate the loop flow, you know, from outside. It's normally pretty difficult. So it's usually, you know, for these lines across border, it's pretty difficult to get it to correct, you know, in the forward process. And so we'll build some model, you know, but of course you have to kind of have some estimated loop flow, you know, for this approach. And we also developed some kind of a simplified coupling approach. So basically, we can formulate the coupling problem, but then when we solve it, we can, for example, using LP relaxation. Of course, you know, European method is to just simply go to the zonal approach, right? So I think within the nodal framework, we can still explore some simplification. For example, like this LP relaxation, we don't solve the unit commitment. We basically just linearize to relax the binary variables. And another way is like maybe ignore some of the interregional transmission, you know, focus on the interregional. So these are the areas we're planning to evaluate. So after we solve this first round, the simplified model, then we can figure out the HVDC schedule and the flow allocation across. I mean, so for the interregional AC line, we can try to figure out the flow allocation for each RTO area. Then they can take this to run a more detailed clearing, you know, within each RTO. And then, so in HVDC, so I'm not going to talk too much about it. The intra-regional HVDC optimization, you know, their formulation, there's some RTOs already implemented that, but there's some interesting problem we identified with a high renewable penetration on the negative price. So we have another project that will look more into that. And then on the interregional HVDC control, there are also kind of different ways you can look at it, you know, whether this HVDC is, whether it will be part of the interchange, right? So that will determine if this DC flow is just to relieve AC congestion, or is it also trying to help more energy transfer across these two areas? You know, depending on the purpose or construct, then the coordination or optimization method can be different. But in general, we feel like if there's a large HVDC network, the best approach would be solve this coupled large area, you know, clearing, and then to figure out the best schedule. It will be pretty challenging to just trying to coordinate and schedule this HVDC in a distributed way. And next is, of course, this multi-stage. We talked a little bit like from day ahead to intraday to real time. You could have a different coordination or solution approach. And then we yesterday we mentioned a little bit, you know, after we tested all these different stages, right? Basically, they had to give you commitment. Real time gave you energy and reserve dispatch. How should we evaluate that? So within Sienna, we also in the process of building something called emulation, basically plugging this commitment dispatch solution, and then ultimately test, you know, what the flow and the reserve deployment will be. You know, what's the production cost, flow violation, and then the combined cost. So here's just one example with this RTS 96 bus system, including HVDC. At this stage, we kind of duplicate the system, make them like a 2 RTO, and then, you know, explore the different multi-stage combination. So here we said they had, if we do the perfect M2M, you know, clearing, and versus no coordination at all on this inter-regional line. And then the third one is the simplified coupling, like we mentioned earlier, to clear them together with LP relaxation and figure out the flow allocation and HVDC schedule, then do the individual RTO clearing. So there's some, I mean, of course, this is a very simple example and very preliminary result. There's some observations like no coordination they had will result in higher real-time production cost and higher real-time flow violation, just like in the middle line. So you see all these bars are higher. So real-time flow violation is much higher. And then, of course, the production cost may be lower because if you may not consider this constraint. But overall, if you add them together, it's a much higher production price violation cost. And then the simplified day-ahead coordination, it actually can achieve similar outcome as the perfect day-ahead joint clearing. So even if we do some simplified coupling day-ahead, it can bring a lot of benefit. And in the end, like in all this approach, you know, real-time coordination can bring benefit, but you know, compared to no coordination in real time. But overall, for this small example, day-ahead coupling can give a much better outcome. So last is on the entry service deliverability, intra and the interregional. The challenge is reserve deployment can have many different scenarios. So like energy power balance, you just have single energy clearing. But when you clear reserve, how it's going to be deployed, there are many different possibilities. Like for contingency reserve, so you essentially you need to consider all the contingency event. You know, after that, how reserve is deployed. So there's a research area basically to identify the right transmission constraint and the relevant event to be formulated or added into the optimization. And then this interregional transmission coordination, this is really getting into real time. Even in the EU, real time, there's no coupling, right? So each RTO will solve the problem independently. But if you observe the flow, you know, interregional flow violation, how are we going to consider reserve deployment as part of it, right? Early on, I showed the result on the energy flow only. the different method can drive the convergence. But if we consider reserve as part of it, it's actually much more complicated. We have some preliminary results. I mean, it's sometimes difficult to converge into the global optimal solution. And another piece of it is like in the multi-stage, really, we should also look into the uncertainty, right? So the reason we have intraday is because the forecast in data may be with high uncertainty, and then if you get better information intraday, you need to re-optimize, and then so we recognize that problem, but at this stage, within the scope of this project, we're not planning to trying to develop a good data set, for the uncertainty. We're just trying to do some kind of reasonable approximation and then reflect that into the multi-stage framework. And finally, it's just a summary. We're building the framework in Siena, focusing on multi-region, multi-stage congestion management, and real-time emulation to consistently measure these different configuration and different solution methods. And also we incorporate intra or interregional HVDC and the reserve deliverability. And then this framework hopefully will help us to analyze the complexity, efficiency, and the reliability. And then this benchmark model will give us, some kind of benchmark, right? What's the best outcome we can achieve? And then really looking to simplify the single large coupling model, and also, the distributed method, the convergence by solving multiple region iteratively. Yeah, with that, end my presentation. And be happy to take any questions.
Sounds like there are no questions. So we can move on to Jose's presentation. He's going to talk about the Siena decomposition on the IRTOC software and development side.
Okay, well, thanks, Yamit. As Junhon mentioned in her presentation, we're working on developing the software architecture required to solve these kinds of models, especially at a larger scale, and with some realistic representation of some of the way that the operators work. So that's been done within the simulation framework called Siena. So for those of you who haven't heard of it, very briefly, Siena, it's a collection of open source packages that we collect in several types of applications depending on what is required. So we have three big buckets of applications. One is Siena Data, which focuses a lot in creating data sets and joining power flow cases with PCM cases. We have Siena Ops, which focuses a lot in the kind of applications we're going to be doing for this project and the type of applications that matter for representing the operations of our systems at different scales. And we have Siena Dynamics, where we focus a lot on the dynamic performance of the systems, including transient stability, EMT, and others. One of the reasons that Siena is being developed inside of the National Lab is because for projects like the ones we're discussing today, for these kind of problems, there's an issue that is known as model limited choice, and is when the situations where researchers or analysts can only formulate and can only perform research that is bounded by the capacities of the models they actually have at hand. There's two classes of model limited choice. One is structural, and is when certain classes of simulation and analysis actually do not exist in the tools that they have at hand. And the second one is when there are formulation limitations, and is the cases where those kind of analysis can be conducted, but they require doing it within the bounds of the existing models. I think that a classical example of a formulation limitation, more limited choice, is that some of the cases where production cost tools don't have the best storage models. So, researchers have to adapt hydro models to be able to do that. And the same for projects like this, where, production cost modeling tools in commercial cases don't have the capacity to model these multi-RTOs. So you require including and making a lot of user-defined constraints. So you could try to simulate the type of behavior that you observe. So Siena is a far more open structure where we can have more flexibility into what we decide. And I just want to motivate one of the cases that we work in Siena this way has to do, for example, in the case of Texas, where, if you want to actually capture the effect of the price adders, you cannot do that with a classical two-stage UC-ED, right? You need to include the UC, you need to include the ED, or the day ahead and the real time, but you also need to include the out-of-market operations. And, in many cases, and especially at the lab, when we want to evaluate merchants, we want to evaluate ancillary services, these simulations start requiring 6, 7, or 8 stages sometimes, so that we can actually represent these kind of behaviors that are outside of a single model. So Power Simulations.jl is the base library where we're developing all of these capabilities. We basically focus on 3 main contributions. One is on the software engineering side. We're trying to define how should we engineer software for applications like this using modern concepts in power systems, in software engineering. We also focus a lot on the power systems modeling. How can we keep the representation of particular power system applications and make the problems still scalable? And of course, mathematical optimization, which allows us to say, how can we solve these problems more effectively? And the way that we formulate an operations model in power system is distinct from classical power production cost models that have like a single monolithic model that employs a lot of switches and parameters such that you can arrive to different kind of models. We actually think about composing those problems and composing those models by collecting a set of cost functions, collecting a set of device by device models that are like distinct from each other at the branch level or the injection device. We couple them together in a particular representation of the network. Then we couple all of the services, and then we use feed forwards as a way of sharing information between different models that have distinct formulations. So what this allows us to do is that, people ask us, what is the model of Siena? Well, in Siena, there's actually no model, right? There's no single model that you use. You compose it depending on what kind of templates you create and you employ. So you can arrive to models that are more similar to MISO, or more similar to CAISO, or more similar to other European markets, depending on how you want to formulate each one of the devices and how do you encode the rules of these systems as part of the resulting model in Siena. So how do we use this, right? So like we go from this set of equations, and this is actually how that looks like. We start from a network model, for example, a PTDF network representation that it has its own assumptions. And then we define, as you can see on the right, how we want to model each one of the components individually and the reserves. So that's how we approach building models in Siena. And that allows us to have a lot of flexibility about how do we want to simulate, for example, if there are different rules for dispatching storage into different RTOs. We can actually say I want an RTO that has its own model of storage and the other one that has a different model. Or if I want to simplify an RTO, I can go into one RTO and say I want to model this one just with some basic dispatch, or I want to model this one with a detailed unit commitment. Right? So the other important concept of how we actually develop software for this kind of applications is that we actually have this three-type structure in how we think about the simulation. As I showed before, every one of the devices has its own model that creates an operational model. And every one of these operational models, again, because it's not monolithic, they're different from each other. So every one of these ones then gets all tied out together inside of a simulation model that combines them, what we call a simulation sequence. And the simulation sequence is the one that defines how these different models share information. One of the innovations that we have in Siena is this type of modeling, right? Because at the end of the day, again, one operation model could be a bunch of merchant operators just submitting bids to the market, and then a separate operation model could be the market clearing, and a separate operation model could be, for example, the supplementary ancillary market. So if you were trying to put all of this complexity into a single monolithic formulation that you modify through switches and parameters, it becomes really unwieldy. So we have here is that we have this kind of disjointed approach and employ the simulation sequence as a way of coordinating them. So how do we formalize this a little bit more? Because it's not just the software, but how we formalize this sequence. So in Siena, we have a distinction between decision models and emulation models. And Yunhong alluded to this a little bit inside of our in the previous presentation. So a decision model essentially is able to make it operates over a horizon most of the time. Of course, you can always make a horizon of length 1, which makes it like a narrow-sighted. But in general, we think about decision models as being having a horizon, and they define an action variable u, which is a decision variable, over a function that takes into account the state of the variable, which is x, and the previous decision. So the previous state of the system, the previous decision was taken, a set of parameters rho, and a forecast, phi t. So like in this case, phi is the forecast available at time t, right? So we issue a decision, every one of the decision models issues a decision u, and then the emulator actually evaluates what is the response of the system to that decision. So we solve this system of equations G, which could be is also most of the time formulated as another optimization problem, but made mostly out of equality constraints. And that emulation model takes the state that solves for the current state of the system, takes into account the previous state of the system, the decision taken for that period, and the realization of the forecast. So in this method, we actually separate the way that we simulate, we think beyond modeling. So like when you think about even the words, it's like production cost modeling. We think beyond production cost modeling and we move more into operations simulation. So we can simulate the operators making decisions with the information they have, this phi t, and making decisions with particular sets of assumptions, and then having a model to evaluate what is the actual response of the system to that decision, right? So in making it analogous to an everyday process, a decision model is similar to you taking your GPS, and we're here in Colorado, so if we want to go and drive to Vail, you can take your decision model, going to tell you this is the route you should be taking, and you should you take a left turn and take this exit in the highway. And an emulation model is actually what happens when you're driving. That you're probably your GPS, as you can see here, like it says it takes about 2 hours to drive to Vail, but if you're driving and 1 hour into your drive, there's a car crash, your emulation model says, okay, how do I adapt now to the fact that I need to take a different route, or the change that there's a change in the time that I expect to get there. So the emulation model is to capture that. So because so much of the processes that Yunhong and the project describes are based on the state estimator and sharing information, this is where the emulation model becomes really critical, because it's kind of like it's like a central model that represents what happens in reality, subject to the imperfect decisions taken by different RTOs. So one of the things that we also do is that we have different strategies to make this scalable and large. One of the ambitions for this project is that we can run this in NTP. So, we formulate a problem in a way that most of the time we're updating the right-hand side of the optimization problem, because we don't require rebuilding the matrix A or refactoring it. So in general, solvers are pretty good at you updating the resolving after updating B. And then the incumbent solution actually speeds up the solution over the next step. So, just to keep a small example here, we observe, even for RTS type size cases, over 30% increase in the speed between actually solving. So this is, for example, a model that has a unit commitment, an economic dispatch, and a power flow for the emulator. And, the difference between rebuilding and not rebuilding changes even about 30% of the speed in like a single laptop. And so here you can see, for about 10 days worth of simulation, you can see that, for example, we have this, 2,280 solves of the power flow as the emulator. So the way that we actually solve multi-stage simulations under this design is that we have, we have the time series, we cache them in memory, we update the parameters of the models up there in the right-hand side, like I described. We update the initial conditions, we solve the decision model, we cache the solution into memory, and then after all of the decisions have been taken in part of the sequence of decisions, we then go back and try to update what is the incumbent decision and solve the optimization problem that tells us what is the current state of the system with the emulator. And in this way, part of the software engineering effort is that we minimize the amount of interactions with the disk or with the, especially in HPC systems or in cloud systems where these writes to disk could be for several types of applications are done over the network. We can optimize those applications to the max. So we don't write LP files, we don't throw CSVs. We actually have this kind of like specialized types of file systems that allows us to do this quite fast and trying to have this balance between memory usage and the speed of compute. For a lot of the process that we use in Siena data, we take a lot, takes a significant amount of effort when we have to develop the software to make these cases, right? At a large scale, we have to combine the network files. In the particular case of this project, we're using the MMWU 20 terabyte case, the generation characteristics from NRELs. We have to get all of the time series for the load, all of the hydro information, and all of the renewable energy coming from REV. All of that is compiled using Siena data into a fairly large system with over 200,000 lines, 190,000, about 90,000 buses. And in some applications, we're able to export to Plexus. Other cases, we just keep it in Siena. And again, I think that Jared was going to talk about in more details about NTP, which is the National Transmission Project, but this is the type of system that we want to solve these problems onto. Now, one of the differences between models of this size and this complexity representing the real life operations of these large interconnected areas when we want to model market to market is the fact that, generally speaking, the academic literature thinks about it in these terms. We have two subsystems, there's an exchange, we want to coordinate that exchange, right? And these two subsystems are the two RTOs or the two ISOs, or just kind of like the two markets that you want to operate. So our objective is to think about how do we develop a simulation platform that actually captures more realistic topologies and more realistic problems that are observed in the system. So like if we stay in this particular type of approach, again, there's plenty of academic literature who has looked into this, has looked into ADMM, decompose it, et cetera. However, in real life, and the data sets that we have built, every one of these subsystems actually is far more complex, right, than just coordinating the unit commitment with the flows in between. Because every subsystem is composed of several balancing areas inside of the RTOs. And then these RTOs, these balancing areas, sometimes will be connected between using AC interchanges that are normally for reliability reasons or for reserves reasons controlled in the flow. But they will also have interfaces that usually are, could be combinations of flows between multiple areas, like for example, at the top, could include HVDC lines, could include AC lines, because they're most of the time defined for, again, reliability or for N-1 limit flows. And more critically to this project, each one of these RTOs can have asynchronous areas within themselves. So we have the RTO. The RTO has their balancing areas where there's some control in the flows inside of the RTO, as well as control between RTOs, which is this black line on the right. I know this slide is quite busy. But then within the whole system, there's also asynchronous regions separated by HVDC lines. So you need to be able to balance the RTOs, the synchronous regions, and within the synchronous regions, the balancing areas. So this makes a lot of complexity when you actually want to calculate in a computationally reasonable way. For example, what are the PTDF, we're using PTDF, what are the actual flows? So if I actually want to calculate correctly the flow of that black line between the two RTOs, I need to be able to balance correctly all of the synchronous regions. And if I want to represent correctly the intra-subsystem, like in intra-RTO, real-life network constraints, then I have to consider all of these interfaces, and these interchanges between areas. And what I want to make clear here is that a common confusion is to confuse what I'm defining in this slide as the interchanges between areas and the interfaces. Whereas an interchange is just a flow between two balancing areas inside of a particular subsystem, the interfaces are a subset of lines from which the total flow going through that is limited. And an interface is not limited only to the lines between areas. It could happen. So like, for example, at the bottom, I put an example where an interface and an interchange share the exact same group of AC lines. And, but in the top, there is another interface that includes one HVDC interface and also one AC interchange. And I mean, in this figure, to keep it reasonable, when I say AC interchange, doesn't mean that that's a line. It could be made of multiple lines that connect the two areas. So we have these different levels of aggregation, right? We have AC interchanges that happen between areas that are made of multiple lines. We have interfaces were also made of multiple lines and could imply flows between multiple areas. And we also have the interchanges that we want to coordinate. In this case, I only included AC, but I think that John Hong already alluded that the fact that we're going to include HVDC, but I didn't want to make the figure more complex. So when we have to build something like that, and we also have to formulate how that looks like, and and the software needs to start tracking all of the details in the formulation, especially if we later want to apply some decomposition scheme. So, the formulation has some sets, and we have the buses, we have the synchronous regions, the balancing areas, all the AC lines. For this particular project, we're stopping at 2-terminal HVDC. We're not including multi-terminal HVDC as HVDC technologies because, first of all, I don't think there's any of multi-terminal HVDC deployed, and the timeline, the schedules to deploy any of that are pretty far away. Again, then we have these inter-area exchanges, which essentially are made of this kind of combinatorial combination of different areas. We have the transmission interfaces, and for the sake of simplicity, I'll just create a single group of generators, but assume that those are like gas and hydro and nuclear and renewables and etc. We have the feasibility sets for those and the time steps. Now, where it starts getting complicated is when we have to start indexing and finding all of the different pieces that make up the models, right? That make up this network formulation. Because we need to distinguish which subset of buses are in a particular synchronous region, which subset of buses are in a particular area. Because, as I mentioned before in this scheme, like we have buses, we need to identify which buses are in the green circle, which buses are in the purple circle, which buses are in the red circle. So we have to index all of those. We have to find which generators are in the green circle, in the red circle, and in the purple circle. We also need to identify which HVDC lines are assigned to each interface and which AC lines are assigned to each interface. We also start needing to identify which buses are the ones that are crossing HVDC, which are the buses from and to of each HVDC line, such that we can tell if a particular bus is in a different synchronous region, but and contributing to the exchanges through HVDC. And we have to do the same not only for synchronous regions, but we have to do it for areas. Is this HVDC an embedded HVDC, but connected between two areas? We also need to identify that for the AC lines, which lines are inside of a particular synchronous region. Now, the good thing about AC lines is that they will never be in between synchronous regions because otherwise it wouldn't be a distinction between the synchronous regions. But we have to identify which lines are in between the different areas and which lines and which exchanges, internet exchanges, are also in between the areas. So this again makes the problem really complicated, because if you think about it from the software perspective, we have to have all of the mappings. We have to map all of these indexes to identify exactly what is connecting what and who belongs in each one of these, circles. We also have different parameters, and in this particular case, because we have asynchronous networks, we also have to calculate a PTDF matrix for every one, a sensitivity matrix for every one of the synchronous regions. So again, we can be back in the situation where, for example, on subsynchronous region 2, we have a single PTDF, but that PTDF is to coordinate the two RTOs, because the exchange happens to be in that synchronous region, right? Then we need to get all the demands per bus. Then we have all of the generators, maximum powers, your maximum flows of your HVDCs, your maximum flows on the lines, your maximum flows in the interfaces, and your maximum flows in the inter-area exchange, right? This is the NSI. I use a little bit of a different notation than Yunhong, but this is the NSI, which again is a collection of branches. So the model formulation, we one of the things that we use in the software is that we actually reutilize a lot of expressions. So in Siena, we're able to keep track of expressions as objects so that we can reuse them. So we keep track of two types of expressions. One is the net injection at a bus. That is essentially the demand minus the generation. And then we include the HVDC here, right? Because the HVDC allows us to calculate the injections that go into the PTDF flows. And then, the flow of every line is essentially the row of the PTDF times the injections of every bus. And for models of the size of NTP, we have to apply a lot of techniques to get these PTDF rows, sparsifying them, reducing the number of lines, collecting buses that are radial. And I'm not going into many details of those, but essentially at the size of the system that we want to solve, this flow is the best estimate we can have, given simplification that need to be done to make the model solvable even by commercial solver standards. So the model formulation at the end of the day, when we collect all of the constraints and collect everything together, we kind of looks like this. So our generators here at the top level, we have the feasibility sets for the different components. We have the generators, we have the lines, we have the HVDCs, and we have the exchanges. All of them have to be feasible, which in most cases for those flows is that they're within the bounds. And the generators have to have, depending on the model that you're using, their minimum up and downs, their ramping, etc. So the first constraint is the synchronous region power balance. So all of the generation in a synchronous region, plus and minus the HVDC input outputs, have to meet the demand for that synchronous region. So that's the baseline constraint. The second constraint that we see now is a power balance over the area. And as I mentioned, one of the tricks that we're using in this formulation is that instead of adding all of the AC lines that connect the different areas, we use this idea of the exchanges that are just like a single flow variable that collects all of the flows of those lines, right? So if you have 3 lines connecting 2 areas, that's the net exchange. The net exchange is this variable for the exchanges. So like, we have our generators in the area minus our flows in and out of HVDCs for the area. Then and then we have the the exchanges, the exchanges in the exchanges through AC, right? And then the total exchanges are the sum of all of the flows of the lines in and out and the sum of the flows of the HVDCs. And I just spotted an error here in my model where like the HVDCs counted twice. So that's probably something I have to fix in the slides. But essentially what we do here is to say like, we balance the synchronous region and we balance the areas, but we use these net exchanges we use these net exchanges that facilitate if we want to share information between the different models and if we want to simplify, right? So we can have a group of lines, even though if we're not modeling all of the lines between the 2 areas being exchanged, we can still restrict the flows by restricting the net exchange. And finally, the last set of constraints are the sum of all of the AC lines and DC lines that make up the interfaces. So we have a maximum and minimum over the interface. So like, again, if you look at this kind of like complexity of balancing all of these areas, to this moment, even though we've conducted significant research on what is the academic approach that exists, this level of balancing is not being explored yet when you have to actually put it like that. So the implementation of the simulation, which is a work in progress, we're trying to implement all of the different methods that Jung-Hong explained, where we do the benchmark model, then doing the coordinated through the flows, and then and then using the values of the system. So what we're implementing is a workflow that looks like this in a new package called Power Simulation Decomposition that will allow us to implement not only some of these methods, but some of the composition methods to scale up future studies similar to NTP, where we can solve this benchmark day ahead problem. We can get from that benchmark day ahead problem the commitments, the responsibilities and ancillary services, the interregional flows. We can fix those, and every one of the simulation of the ED steps, we can read. I mean, and this diagram is only showing 2 regions. Like if you might make it more regions, of course, it grows in complexity. But we read variables from the state, and then solve the decomposed problem in R1 and R2, update the power outputs of those, solve for the emulator, where we could even inject uncertainty, right? So like we can solve the ED with a particular forecast, but then inject a different realization of the renewables, such that this effect of using the previous time step from the state estimator, we can include effects of having deviations from the state estimation versus reality in the emulator, and we can solve this problem. So at each step of the economic dispatch, we evaluate all of the variables in a disjointed fashion to different problems that are solved independently, and then update the emulator to simulate the effect of the state estimation. And then solving these problems at a large scale requires several tricks for scalability. Like on the one hand, reduce radial branches of the PTDF and specify the matrices, so we can simplify the construction of the expressions for the flows. We're also exploring the use of word equivalents, such that even though in practice the two RTOs have visibility over the whole PTDF, you're still using a lot of information from the other RTO that makes it, you're still calculating a lot of flows in the other area. So the question is, can we actually, for the disjointed method, use word equivalents such that you can calculate your local flows and the flows in the neighborhood of the interchange you're trying to optimize, but you don't calculate flows further away from you that belong to the other RTO, making the system faster. And then we also parallelize the build and solve of each decomposed problem. So thank you very much. Again, we keep working on this. This project is pretty exciting for us from the software perspective. It's probably one of the more complex ones we're working on these days. And check out Sienna. And we're gonna keep updating the package to hopefully make the coding production quality such that these kind of simulations can be conducted, given the interest in regional transmission coordination. These type of developments are pretty important because there are not that many tools out there that try to formalize this type of operational simulations. I don't know if there's any questions.
Thanks, Jose. We'll move on to Jared before we get into more discussions.
Okay.
So thanks for the great presentation on the software. And now we'll introduce Jared Wright, who will discuss the case studies for the IRTOC project in some more details.
Thanks, Jan. Just want to confirm that you can see my screen with audio as well, and you can hear me. Okay, great. Yeah, so I'm going to try and talk through a little bit of a specific case study, but maybe just providing some context that would frame that more specifically for the purposes of this IRTOC project, and that is the National Transmission Planning Study. David had already presented maybe the sort of 50,000-foot view of what NTP is, what the objectives have been, and also some ideas of sort of the forthcoming publications that are coming from NTP. Similarly, Christina also spoke about some of the companion reports or at least papers that are also coming from it. What I'm going to specifically focus in on here is the context of NTP as a case study and building from what we did within the National Transmission Planning Study to then take some of those large-scale models and test these algorithms that we've been talking about for the last hour and a half or 2 hours or so at large scale. So really building on what we did in NTP, providing the background on what we did in NTP, specifically in this nodal space, and then getting an idea or trying to give a feel for some of those key outcomes that we starting to see as part of the NTP. And then finally, how we're going to build on that and use it for IRTOC. So the first thing that I wanted to say is we want to start by, and I just wanted to remind everyone sort of in terms of these coordination configurations and the types of constraints that we would like to be imposing and controlling across the multiple RTOs. These 11 that Yonghong had already spoken about, 2 and 8 being where IRTOC is intentionally going to be focusing in on. And then, of course, the example of where interchange optimization is C1 will be on C2 and C8 in terms of the coordination configurations. And when you have all of those constraints included, which is obviously very difficult to do, especially at large scale, would be that sort of C11 type of configuration where you have full multi-area coupling across multiple RTOs. This is only for information, and of course, this had already been described, but I thought it'd be important to just remind everyone of level setting as to where we intentionally focusing our attention as part of this specific project. And again, as Yonghong had mentioned already, the project so far has gone from the left to the right-hand side, but not necessarily to the complete right-hand side. So 5 bus test systems, 96 bus RTS test systems, and then going towards this subset of the Eastern Interconnection, which would be in the order of thousands to potentially tens of thousands of buses, depending on the part of the EI that we'd like to focus in on. And saying that we do want to focus in on a subset of the Eastern Interconnection, likely the regions between MISO, PJM, MISO, SPP, and making sure that as we walk through these different levels and take the crawling, walking, then running type of approach, there may be some intermediary steps before we go to that large scale. So I just wanted to note that here as well. Of course, the project is still in progress, and we'll see how we go through the levels of complexity we see and the computational challenges that we potentially see as we implement in software, specifically in Sienna, that Jose had provided now, that background, a consistent evaluation of the economic as well as reliability impact. So how complex is it going to be? How tractable are these models? The efficiencies, so looking at production cost as an example of that in that emulation type of environment. And then, of course, reliability impact, so the potential for shortages or relative sort of flow violations between regions. Now, more specifically on that subset of the EI, this just gives you a summary from NTP where we are leaving off. The temporal resolution for the production cost modeling at a nodal level within the NTP project was a combination of the Eastern Interconnect work as well as ERCOT, actually. But just for the purposes of today, I'm focusing in on the EI, where there's about 96,000 buses, 120,000 lines and transformers, 8,000 generators and storage components, as well as then about 41,000 individual loads distributed across the relevant nodes based on the power flow cases that establish that. The temporal resolution for the exercise that we undertook as part of the nodal PCM, and I'll show where this sort of fits in overall as part of NTP, is hourly, 7 steps, so 1 week at a time, 52 weeks being solved in parallel, and the horizon's 24 hours with an overlap of 48 hours. Now, I'm mentioning stages there for the CONUS or contiguous US type of run, where we include each of the 3 interconnects. And those stages, I'll explain in the next slide, a few slides in this next following section. But effectively what it is starting to increasingly represent or better represent transmission constraints. And for the purposes of NTP, the intentional focus was interregional. So we focused in on those interface bounds between regions, and specifically what we've defined as sort of the FERC 1000 planning regions, including ERCOT, but subsections of each of those in order to have some better spatial granularity. And I've given some information there around the interface bounds that were in the existing models, or let's say the starting points, as well as then particular scenarios. I'll describe the 3 scenarios that we down translated into nodal models as well in the next few slides, as well as then the types of boundings that we had as part of that to give you an idea of the type of complexity on the production cost modeling side and the interface flows that we see. To give you a feel for the solve times as part of those stage 1 runs in the order of 2 to 4 hours, for the stages 2 and stage 3, 18 to 30 hours, depending on the scenarios. So just keeping in mind here, and that's why I put it in the bottom right, this is a global co-optimization of energy and reserves, and it has perfect foresight. So not necessarily a multi-stage, but a single stage day ahead at an hourly resolution. So to just give you a feel for these NTP nodal scenarios, this was the intention of NTP. And that's why I say this is where we're building off and sort of jumping off from, is we take nodal starting points or industry planning cases. We have these capacity expansion scenarios that David was talking about a bit earlier this morning, which are at that zonal level of resolution. We have an idea of the interfaces between each of these zones and how they are going to be expanding as a function of the various input assumptions and those sensitivities that he was describing. Generation and transmission are then traded off as to getting towards those least cost outcomes on the basis of input assumptions. What we do then is we take a specific scenario as well as those nodal starting points, those industry planning places, and undertake a zonal to nodal translation where we have this future representation with a very different resource mix, as well as a representation of this interzonal transfer capacity between the various zones. And for the purposes of NTP, those zones, there's 134 of them across the contiguous US. I'm just showing a few here just to give you an illustration of those outcomes where we build a very different resource mix as a result of the capacity expansion scenario. We then have distinct individual expansions, new interregional branches that are shown in the dotted lines there, as well as new intra-regional types of branches that are defined by the scenario to then get towards the outcome that's representing as much as possible going towards the capacity expansion scenario in terms of curtailment, production cost, the resource mix, in terms of installed capacity. Of course, the energy dispatch is quite different between them as you're starting to represent more temporal constraints in the production cost environment than you were in that capacity expansion environment. But the real purpose of the zonal to nodal translation is really to get towards the transmission expansion needs. We get a better appreciation of the transmission expansion needs at a nodal level of detail. And I'll try and just briefly talk through the three scenarios here. The next slide is actually more important. This is a quick summary, maps at the top across the three limited AC and multi-terminal HVDC scenarios from NTP. And this is from 2035 for 90% reduction by 2035 of CO2 emissions in the power sector. There's a summary at the bottom as well across each of the main sort of 4,000 transmission planning regions, aggregated up, as well on the left-hand side of each of those graphics to give you a feel for the total installed capacity by 2035, as well as then those maps give you an idea of, okay, well, where is it going to be? Where's a lot of the new resources going to be in terms of the outcomes you'll see here, more solar, lots of wind, as well as then where are generators likely to be deactivated or decommissioned as part of some of these futures that we're seeing. These are the three scenarios. This is just the disaggregation of the generation capacity component of that, of which in this next slide is where I talk to, well, how do we actually now expand the transmission? And this was those stage 1, stage 2, and stage 3 that I was describing a few slides ago, where we have this initial performance assessment where we unconstrain the nodal production cost model. We also then actually run a semi-constrained or a semi-bounded type of transmission constrained nodal PCM where we don't necessarily bound individual branches, but we bound interfaces. And those interfaces are between these FERC 1000 transmission planning regions. So what we start to get a feel for there is where does the power really want to flow as a function of the new resources that have been added, as well as generators and storage that have been added or removed as part of these futures. So we get that initial understanding and we then translate that into a set of snapshots. And that's what I mentioned at the bottom of this slide here. But those set of snapshots are then run in a linear power flow, DC power flow. We take the information from that and expand the transmission in that inner loop between the sort of green or teal as well as the blue color, that transmission expansion exercise. And the tools that we use as part of that, I won't necessarily go into today. That iterative process is a combination of using typical classical, the industry power planning tools like PSSE, as well as then some spatial tools, so GIS tools to enable us to see where power is flowing. That visualization tool that David showed earlier also assists us in understanding where the power is wanting to flow. We do the transmission expansion to try and alleviate overloads. Once we've gone through the stage 2 expansion, we pass that additional transmission expansion back into that outer loop, into the orange transmission constrained nodal PCM, and run this again, starting to increasingly better represent or refine the treatment of nodal transmission. And this is under normal conditions or N-0 in classical transmission expansion planning parlance. We then go towards a stage 3, where we also undertake a similar iterative transmission expansion exercise, but for single selected contingencies. And those single contingencies for NTP were those that were along the major interfaces between each of these FERC 1000 planning regions, transmission planning regions, as well as then primary buses back from that, so single buses back from that into the individual transmission planning regions. Similar exercise, linear power flow, and then sending that information back into a transmission constrained nodal PCM, where further strengthening may be necessary as part of that stage. And of course, you can start to see that stage 1, stage 2, stage 3, you can also foresee a potential future stage 4, where you do AC power flow, potential stage 5, where we start to look at dynamics and start to think about the additional mitigation measures, equipment, transmission potentially that may be able to be installed to then get towards some kind of feasible futures. And those feasible futures I'm going to run through in the next 2 slides, but not necessarily for the intention of sharing the NTP nodal solutions and outcomes. A lot of that will be published during the back end of summer this year, but primarily for the intention of just sharing an understanding of the types of futures that we're seeing in terms of interregional transmission expansion. And this will be used as, or we intend to use parts of the EI, in this specific case, the AC transmission expansion in 2035. We intend to use part of this as part of the IRTOC project, so leveraging off what had already been done to then really get a deeper understanding of not necessarily this perfect foresight day ahead hourly nodal production cost, but also going into more detail around the various coordination configurations that we've been speaking about. So just to give you a brief overview of these futures and these expansions, we did intentionally focus on interregional transmission, as I was mentioning, but at the same time, any enabling intra-regional transmission is also expanded. So getting localized pockets of new resources out and towards load centers, moving power across regions that are not necessarily adjacent to each other. So they need to move a lot of power, for example, from SPP across MISO towards PJM, and potentially also from Florida into the southeast, and the inverse from SPP and MISO down into the southeast and FRCC, for example, when looking at the EI. Now, what we see particularly in this scenario is a lot of 500 kV being extended across into SPP, where of course the 345 kV networks are predominant at the moment. And you'll see that across some of the major interfaces, SPP North, MISO North, SPP South, as well as MISO Central, and then from SPP South down and across through that MISO South region and into the southeast, where a lot of 500 kV is expanded, but on the basis of the existing 500 kV network that's already there. And we also have some selected intra-regional 345 kV expansions, and then of course you'll see some of the existing 765 kV are expanded from single circuits to double circuits. And of course, just keeping in mind, this is a single realization of a single particular scenario in a single year to give a feel for the types of feasible transmission solutions that we could see for this particular scenario, for this AC transmission expansion scenario that David was previously describing. And then I'll just go through the second one here, which then starts to bring in the HVDC component. So multi-terminal HVDC expansion, the orange is the HVDC, the colors on the AC side are as before, so green being 345, red being 500 kV, and then the purple 765. So you can see in this type of a scenario, number one, of course, as we were describing in the zonal results previously this morning, seems crossing capacity is expanded quite substantially between SPP as well as Northern Grid, SPP West Connect, as well as then between ERCOT and West Connect, and then ERCOT and back into the EI, up into SPP, as well as into the southern parts of MISO. But what's also important here is the supporting high voltage AC transmission that's needed to support these types of expansions. So it's not necessarily just the HVDC that's expanded as part of these. We want to see the type of HVAC as well, whether that's intra-regional to collect and send bulk amounts of power across longer distances, or whether that's to support for contingency performance when you have large outages on HVDC parts of the network, that you can still transfer power interregionally across the major regions where you see the dominance of the HVDC networks. Very similar to, as you can expect, because we use the capacity expansion zonal outcomes that you're seeing here, but this is now the specific nodal realization of that. And the starting points of number one, multi-terminal HVDC networks already by 2035, as well as in some cases, for example, in West Connect, parts of SPP, already the potential for meshed HVDC. And operations within those, of course, I'll start to talk about next, but just important to remember that, of course, that will be quite novel in terms of operational challenges and opportunities. And this is a quick summary across each of these regions, across these three, across each of the regions, CONUS-wide from NTP, the types of net interchange over demand. So it's normalized to the demand, exports being on the positive side, imports being on the negative side. Of course, as you can note, several regions move power in one predominant direction as exports. So SPP, MISO, WestConnect. Similarly, IRTOC, of course, is going to be looking like they're exporting a lot of power when you start to enable that HVDC links across into WEC, parts of WEC, as well as into the EI. But several regions also move power in both directions. As imports, and then some other regions as move power in both directions. So regions that are predominantly importing, CAISO, PJM, New York ISO, and then others that move power bidirectionally. So the likes of Northern Grid, the Southeast, FRCC, ISO New England, you can see that sort of bidirectional flow throughout the course of the year. Now, as I was mentioning, these are those idealized day-ahead types of interfaces and the types of flows that you then see. And as part of IRTOC, the intention is now to start to think of different operational coordination mechanisms and start to test that at scale for some subset of the Eastern Interconnect. So the SPP MISO, the MISO PGM types of interfaces and the types of flows that we would then actually see when moving from these decision models towards these emulation models and starting to actually emulate those and the coordination mechanisms that support it. So to talk briefly, some of the key takeaways, there's really just three here for now. There are many more that will be forthcoming. But firstly, lots of opportunities as well as potential challenges. I was mentioning those for our ISOs and RTOs on this interregional coordination need. The high voltage AC and HVDC that's embedded as part of that work together to improve contingency performance. That expanded interregional transmission also means that we need to start to investigate it, which is what we're doing as part of this project. New potential operational frameworks to deal with these configurations, so multi-terminal, meshed HVDC, and how that links in with the supporting underlying embedded HVAC networks. And then in these in the AC and multi-terminal HVDC scenarios, we do see more variation. I summarized that in the previous slide. We have a lot more information forthcoming, but I think for the purposes of this project, some regions become big importers and exporters. That's what we're focusing on this particular subset. Some are quite balanced, so it's not necessarily that they import or export large amounts, but they're quite balanced. And some do import and export during the year at different periods, so we want to analyze those interesting regions. We do see larger swings diurnally, so this will be interesting to analyze further as well, driven by lots of solar PV and storage in particular regions. And we do see larger absolute power exchanges, of course, and that's intentional and part of the design of the scenarios that were then down translated. So relative to that limited inter-regional type of expansion, we see long distance, large power transfers that are needed, increased number of interregional tie lines, and then of course the potential for new voltage overlays. So moving from 345 kV to 500 kV, potentially 765, as well as then as part of the HVDC scenario, the deployment of HVDC and multi-terminal and potentially mesh types of configurations. So we think that the NTP interregional scenarios could be useful starting points for further assessments of these sort of multi-stage and multi-region operational problems. And that's really what I just wanted to talk through in this last slide. Just in a few bullet points where we're going to intentionally focus on that subset of the EI. We don't necessarily have a particular decision on which parts and which subset of that. For now, we're thinking SPP MISO or MISO PJM, or a combination of those. But if you remember towards the first few slides of this presentation, that scale starts to go towards thousands, tens of thousands of nodes. And of course, the problem in terms of computation and binding constraints becomes something that we want to be thinking about quite carefully. But the benchmark that we expect in terms of this large-scale implementation is to choose the appropriate NTP scenario, have this global co-optimization of the energy and reserves, perfect day-ahead. Foresight is what we have at the moment, so you could think of it as almost that C7 type of configuration, if you remember back to, I think it was slide 3, CONUS-wide. And this will be the basis to then derive these sub-regional interchanges and reserve requirements for understanding those coordinations, operational coordination scenarios that we're thinking about. So C2 and C8 as those configurations. We do, and I just wanted to note these in a few bullet points here, is that when implementing at this large scale, we do anticipate some computational challenges, probably not some, but many. We do anticipate potential convergence challenges on some of the distributed algorithms, and I think Johan spoke to that generally already as part of the test systems that we've been testing on. So coordinating a large number of constraints, we do see that we're going to have to test some of the different algorithms as part of the different operational configurations. We want to think of really using a small number of constraints initially and then generate the insights, using the framework and the models that are built and the benchmarks that are built to then be utilized for future potential sort of production use and broader scale development. But the intention of this project is to understand and get a feeling for the types of coordination configurations, the performance that we see, starting to make some key decisions potentially and recommendations as a result of that in terms of the complexity of the different options, day ahead, real time, a day ahead, intraday, and then real time, in terms of the multi-stage approach, as well as then the multi-region approaches and the algorithms that support that. And just to highlight one last part in terms of the imperfect foresight and these look ahead, day ahead versus intraday types of realizations, is this forecast uncertainty is not necessarily something that's a part of our focus, but we want to be using some reasonable estimates for that. So we researching those topics at the moment and thinking about the types of data sets and time series profiles that we're going to be using as part of that. But the intention is not to focus on that levels of uncertainty and the types of data and time series that could support that, but just to use reasonable estimates to get an understanding across the various configurations, as well as the multi-stage operations, the types of performance we can see. And I think that is all for me. So I will stop sharing and go into Q&A.
Yes, and Yami, GDO may have more conversation with all this effort, and then yeah, I think after we build this tool, it'd be great if we can use that for some studies or some use case. You know, some of the issue they have, or I mean, these entities have encountered.
Yes, yeah, definitely excited, yeah, to keep in touch and hopefully, yeah, we want the ultimate goal is for these process improvements to reach industry. So if and it's been a long day and long 2 days, so I think we'll probably cut it here unless anybody has anything burning to say, and we'll post, yeah, like I mentioned, we'll post a recording and the slides in a couple weeks, and if folks have additional questions along with the recording and posting, we can include an email address that y'all can send questions to or comments.
Is there a particular contact person that GDO would like to have for this? Who do we reach out to?
You can send me an email if you want to send one to GDO, and I'll put my email in the chat, and you can also send Yonghang an email as our NREL PI.
Thank you. And thank you for your efforts.
Yep. Thank you.
And as Yonghang, you can put your email in the chat as well.
Sure.
If you're interested. And yes, that's all we have for today. So yeah, thanks everyone for all the great presentations and for the engagement over the last couple of days. And we appreciate, and we'll keep everybody apprised as we go forward.
Great. Thank you very much.
Thank you.